Good day, esteemed professor and colleagues. On behalf of our team Nightingale, it is my great honor to present our project entitled Battery-Free Wireless Flexible Smart Bandage for Pitch-Guided Wound Care. This research was conducted at the Wireless Soft Electronic Laboratory, Department of Electronic Convergence Engineering, Kwangwon University, under the supervision of Professor Chang-hyun Kim. Today, I will introduce the motivation, describe our systems, and highlight our main findings. Chronic wounds are a serious health concern, unlike acute wounds, which heal in weeks. Chronic wounds often persist for months. In the US, around 6.5 million people suffer from them each year, with higher mortality and an economic burden of up to $97 billion annually. The global market for wound care is projected to reach $25.2 billion by 2032, showing the urgent need for more effective solutions. Chronic wounds can deteriorate within hours, making early detection critical. Real-time monitoring of wounds, which can serve as an early warning of infection and reduce the need for frequent hospital visits. Our objective is to create a battery-free, NFC-based smart bandage that monitors pH and transmits data directly to smartphone and even enable on-demand drug release. Our system combines three main components: an LIG pH sensor, the RF430 NFC chip, and the MT3608 boost converter. The workflow is simple. The pH sensor detected the wound environment. The RF430 processes the signal and determines whether a treat is needed. If yes, it activated the MT3608 boosting voltage to power the heating pad. The heating pad then triggers drug release. All of this is powered wirelessly via NFC with no battery required. The RF430 chips is the central part of our system. It harvests energy directly from a smartphone, integrates ADC, and transmits sensor data wirelessly. Compact and low power, it is well suited for wearable healthcare applications and enable both power harvesting and data processing in our bandage. The LIG pH sensor uses a 3-electrode structure. For pH monitoring, the working and reference electrode are used to detect voltage changes linked to wound conditions. Since harvest NFC power is not sufficient to drive the heating pad, the MT3608 boost converter raises the voltage. Controlled by the RF430, it activates the heating pad when treatment is required, enabling on-demand drug release.
This slide shows our final circuit design. The circuit is composed of three main blocks: the NFC sensing and communication block, the pH sensor analog input block, and the boost converter with heating and drug release control block. First, at the center of the circuit is the RF430 FRL152H. Its antenna 1 and antenna 2 pins are connected to the NFC coil, matched to resonate at 13.56 MHz, which allows for both wireless power harvesting and data communication. For sensing, we use the LIG-based pH electrode to measure its open circuit potential. ADC0 is connected to the working electrode and SVSS is connected to the reference electrode. Here, SVSS functions as the analog ground, providing a stable reference potential. The measurement follows an open circuit configuration, meaning no bias is applied. In this way, lower pH results in a larger potential difference and higher ADC voltage, while higher pH reduces the potential difference, leading to lower ADC voltage. Next, on the lower left is the MT3608 boost converter. Its EM pins controlled by a GPIO of the RF430, enabling on-off switching through software. This power is then supplied to the heating pad and is activated only when the sensed pH exceeds a defined threshold. Regarding the drug release layer, the threshold can be adjusted in software using the calibration curve. The circuit was fabricated on a flexible printed circuit board. This design choice ensures both durability and flexibility, which are crucial for close attachment to the wound area and tolerance to body movement. On the left diagram, the layout was created in AutoCAD. On the right diagram, to pattern the FPCB, we fabricated a custom mask. Now let me explain the FPCB fabrication process step by step. We begin by preparing an FPCB copper-colored substrate of the appropriate size. The copper surface is cleaned with isopropanol. We spin coat AZ4630 positive PR for 40 seconds. Soft baking removes solvent and improves photo stability. Using the fabricate mask, we expose the PR with a mask aligner since it is a positive resist. The exposed regions will later be removed. The exposed PR is removed using a developer solution, revealing the copper trace pattern. The remaining PR is hardened to increase etch resistance. If insufficient, undercutting can occur during etching hard bake. We then use a CUH to remove the exposed copper. Finally, we inspect the fabricate circuit under a microscope for the defects such as open shorts, bleeding, or undercutting.
Project focused on developing a smart band system using the RF430FRL152H chip, a LI-based pH sensor, and the MT3608 boost converter. In the development process, the RF430 cannot be directly debugged with a PC, so we used the MSP pen module. Since CCS does not fully support RF430, we applied TI-dedicated firmware. We configured memory and NFC data transfer using linker and NDEF file, and implemented in main C the workflow of pH sensor input, ADC converter, threshold compression, control signal output. The NFC communication operated stably at 13.56 MHz. The pH sensor successfully detected voltage changes according to pH levels, and the MT3608 booster converter generated higher voltage reliably. With CCS, we also confirm on and off control. Experimentally, the voltage was 0.107 voltage at pH 4 and 0.083 voltage at pH 7, showing a clear trend of decreasing voltage with increasing pH. There are still limitations, debugging issues in standalone environments, and potential external risk in real-world conditions. Future work will focus on advanced control algorithms and biocompatible packaging improvement.